Hello. I think I may have misspoken on the last slideshow. I think I said that was the last lesson in the chapter, and it, as you can see, is not. We are in Chapter 2, Lesson 6 today. In Lesson 5, we talked about the system of geometry and the different parts to it. We said we needed to start with some definitions, undefined terms, postulates, do you recall those? Statements we accept without proof. And then we mentioned theorems. Well, today we're going to talk about a couple of famous theorems and then the problem set. It's going to get you to practice with those theorems. Here's one of them. Peter is teaching a geometry class. Anybody heard of the Pythagorean theorem? And that's about the only thing this cartoon is worth because it's kind of strange. So a bright young lady comes up. You mean about the square of the hypotenuse being equal to the sum of the squares of the other two sides? I have. The expression on his face tells he's not real happy, so you may go clap the erasers. Not what you should do with bright students. Punish them. But here is a picture of the Pythagorean theorem. And you might say, hey, that does not look much like the Pythagorean theorem that we had when we were in school or in algebra. That probably looked more like this. You said a squared plus b squared. I do not write well with a mouse. Equals c squared. You know what? I'm going to take a minute and see if I can write any better with this tablet. Does it work? I should not be wasting your time. You can't even see it. Oh, there it is. So, a squared plus b squared, a little bit better, but not much. C squared. That look familiar, even though it doesn't look very clean. So what exactly does that mean? A squared plus b squared equals c squared. Well, today we're going to take a geometry look at it. It has to start with a right triangle. That's what we have right here, this yellow triangle, a right angle here. And you may or may not know, but the two, this and this side, A and B, are called the legs. The two that include the right angle here, or surround that right angle, those are the legs. And this is the hypotenuse. The longest side of a right triangle, it's always opposite the right angle. And here we've drawn a square on leg A. And of course the area of that square, since it's a square, is A times A, or A squared. We've drawn a square on the other leg whose length is B. Since it's a square, it would be B times B, or the area of this square would be B squared. So if we add the areas of these two squares drawn on the legs together, the Pythagorean theorem says that if you take the hypotenuse and draw a square on it and find the area, since it's a square, it would be C times C, or C squared, those two would be equal. In other words, the area of the squares on the legs is equal to the area on the hypotenuse. What follows is a brief demonstration of that. It doesn't prove it. We're just trying to demonstrate that idea. So what we've done is we've created a square that has the red square inside of it, along with 4 yellow right triangles. Those triangles are the same as the original triangle here. Now if we take those triangles and we move them down into this other part, you can see again we have those same 4 right triangles. This one didn't move. And now instead of the red square, we have the blue square and the green square. So here they are, both of them. You can see we've just taken those triangles and moved them over. How does this demonstrate the Pythagorean theorem? Well, if I move these on top, you can see the squares are exactly the same size. So they would have the same area. And if we were to take out these four yellow triangles out of each of them, what's left? Well, the area of these two squares has to be equal to the area of that square. So it's just a demonstration. Later this year we'll have several good proofs of it. Here's a second theorem. Many of you talked about this one earlier in class. The idea that the sum of the measures of the angles of any triangle is 180 degrees. I think we even demonstrated this in Geometry Sketchpad earlier this year. Again, this is not a proof, it's a demonstration, but maybe you can see what's been done here. Tore off angle 1, stuck it over here next to angle 2, which is in its same location. Did the same with angle 3, tore it off and stuck it in here. So now when you put angles 1, 2, and 3 together, you end up with a straight line, which is 180 degrees. If you're not sure about that, the other side is also 180 degrees, so you get all the way around. We'll give you 360, or a circle. The other theorems we're going to work with today have to do with finding the circumference of a circle and finding the area of a circle. I think these are familiar to you. The circumference of a circle all the way around is equal to pi times its diameter. Again, we prove this in much more detail later. And the area of a circle is pi times its radius squared. We can expand this equation just a little bit here. If we remember that diameter is the same as 2 radii. So where we originally had circumference is pi times diameter, if diameter is 2 radii, we can substitute this 2 radii in for the diameter, and we get a second equation for circumference is equal to 2 pi times radius. That's it for this lesson. This assignment then, you're going to have a chance to practice each of those theorems. First one here, do your best on this, just trying to figure out, do you know what the C stands for? In a survey of 10 mathematical formulas that change the face of the world, here's one of them. E equals mc squared. Do you recognize that? The second was a squared plus b squared is c squared, or our Pythagorean theorem. They think it's interesting to note that c squared is in each of them. Is it related? I don't know. So some questions here. Do you know what the c stands for in each of these equations? You may have to look up one of them. Which country do you think would have a stamp with this type of design on it? Well, it tells us right here, it's a Greek stamp. And one of the theorems is demonstrated right here. Hopefully you can tell by seeing that right triangle. And the squares constructed on its legs and hypotenuse. So first of all, which theorem is it? And then an interesting question. How do the checkerboard patterns help demonstrate or illustrate the theorem? So work that one through. 8 through 10 directly discusses the theorem that we saw in our lesson. They actually show you tearing those off. So read through this and answer those 3 questions. Next, we have a target here that consists of a bunch of circles. We call them concentric circles because they have the same center. Smaller one, larger one, and so on. Each one of them is going to have a little different radius. Here's one radius. The next largest circle has that as a radius. And the third purple circle has that as a radius, and so on. And they give us the fact that the radii are 1, and then 2, and then 3. So it looks like there's 1 unit between each of these rings. Again, spend time with the directions before you get into the problems. Very good habit to get into. So now you answer questions. Here he wants to see whether you understand how diameter relates to radius, and then calculating circumference to recall the equation. There it is, pi times diameter. Or you could use 2 times radius instead of diameter. Up to you. Finding the area of the purple region. Not too bad. That's just a circle here, and you can find the radius. Pi times radius squared. This one's a little trickier. The exact area of the yellow region. Now, why can't you just use pi r squared? Well, none of this part in the middle is yellow. So how are you going to figure out the area of just this circle? That'll take you a little bit there. Again, you're going to use area as pi times radius squared, but you're going to need to do a little bit more than that. And then finally, why do you suppose this is in a book on optical illusions? May not make sense until you figure out the answers to 13 and 14. The next 3 problems, I guess it's only 2, they have you work with the Pythagorean theorem that the square on one leg plus the square on the other leg equals the square on the third leg. Pretty straightforward on 16. Be careful on number 17. Here's the hypotenuse, and here's the square on that leg. So I'll tell you, it's not 25 squared plus 169 squared. Take your time with that. So here we have a bird flying down here, and there's his wing. And we've got some given here. When a bird is gliding, its wings produce a lifting force that makes a 90-degree angle with the direction of airflow at the leading edge of the wing. So here's a diagram. The air is flowing like this, and the wing makes a lifting force right here at a 90-degree angle with the airflow. So we've got a triangle formed here, and they have some givens here. They want you to find A in each case here, and they're giving you the fact that J is 60. Find A. If J is 45, find A. And then find A in terms of N. If J is N degrees, what's A? Working with the idea of triangle angle sum, 180 degrees is the sum of the angles. Here's another one working with that. But we've got these 2 angles A and B are equal. We're going to learn that you call that an isosceles triangle a little bit later. And again, find A if C is 40. So now we've got 40 degrees up here, and these 2 angles are equal. And we're told that this one's 40. Then we're told that it's 50 on number 22. Then they want you to do it in terms of N. Let's say this is N. What would measure of angle A be in that case? Next, notice that the Pythagorean theorem consists of more than simply a squared plus b squared is c squared. Expressed as a conditional statement about the figure shown below, so I'm thinking conditional statement, there must be an if and a then involved. So good practice reading directions. Try to do that one yourself. If, how would it sound? And then look down here. If this figure is a right triangle with hypotenuse c, then a squared plus b squared is c squared. It's a pretty good conditional statement about the Pythagorean theorem. Given that this statement right here is true, does it necessarily follow that if a squared plus b squared is c squared, then this figure is a right triangle? Think about that one a little bit. They're saying if it's a right triangle, then this is true. Now they're saying if that's true, then it's a right triangle. Think about the relationship of those two and then decide whether you think it's necessarily true and tell why or why not. Next, we're working with the theorems about diameter, circumference, area. There's some given here. The widest that your eye, the pupil, can get is 8 millimeters. It's when it's dark out. If it's really bright, it'll go all the way down to 2 millimeters. Lord made it that the eye doesn't allow too much light into your eye to damage it, but allows it to open enough when you need to see in dim light. So now they're asking about area if the diameter is those two numbers. Then just compare. Approximately how many times as much light does the pupil let in when it's biggest as when it is smallest? So you're comparing the areas, and you're looking probably for a fraction or a number that tells how many times more or less. So here we're using the triangle angle sum theorem. That's the idea that the sum of the measures of an angle is 180 degrees. And now just think these questions through. If one angle of a triangle is 90, what is the sum of the other two? If all three angles are equal, how large is each? Remember, we're starting with the fact that the sum of the measures of the angles is 180. Could a triangle have two 90-degree angles? Why or why not? Could one of the angles be 179 degrees? And explain why or why not. So 2 points on those last two. Be careful. More on that. If two angles of one triangle are equal to two angles of another triangle, let's say A and F are equal, and angles C and E are equal, does it follow that the third pair of angles have to be equal? With a little explanation, why or why not? All right, next we have an Indian geometer in a book he wrote, Manual of the Chord. So it's about a stretched chord. So he's starting with this square right here that I just traced. He says if you stretch a chord across the diagonal of a square, which he's done, AB, the chord, AB, is the side of a square, that would be this dark green one, side of a square, double the area of the original square. So he's suggesting that this dark green square is double this original square. Does that look logical to you? So he goes on, if the side of the original square is A, like he has marked here, what is the area of that original square? Now think about your equation for area of a square. What is the combined area of the two light green squares? Combined areas. So the side is A and this side is A. Find the area of that one and the area of that one, combine them. What is the area of the dark green square? And how do you know that? It's just a little bit larger picture for you to look at on this one. So does that demonstrate that this dark green square is twice the size of this original square? I hope you figured that out, that this square and this square appear to be the same size as this square. Well, they'd have to be, because we've got A on each side. I don't know if anybody else thought about, if you draw this segment and this segment, you end up with 4 little right triangles. And if you look at this square, you end up with 2 little right triangles. Doesn't prove it, but it demonstrates it. So here we've got this interesting triangle. We've got a pencil line here, and it's hard to tell, but there's a sharpened point right there. So what happens is they just rotate this pencil as shown by the arrows. First they flip it up there. Now you see it. And they slide it up, put the point up there, and rotate it down onto the third side of the triangle. And then they slide it down, and rotate it back down here. Then you take a look at the pencil right here, and there's the point there. And here it started there. In what direction is the pencil pointing at the end? And what does this direction suggest about the number of degrees through which the pencil has turned in pivoting about the three angles? Ah, interesting demonstration. What do you see in there? Do you have an answer? What theorem does it seem to demonstrate? Next, another Indian, Aryabhata. He wrote this: the area of a circle is half of the circumference multiplied by half of the diameter. See if you can write that equation out. The area of a circle is half of the circumference multiplied by half of the diameter. He wants to know if that statement makes sense, and you're supposed to demonstrate it. This will be using some algebra. Spoiler alert, next slide is going to give you the answer, so pause and try it for yourself. See if you can get it. I suggest working backwards a little bit. I wrote area is half of the circumference times half of the diameter. That's what he said. Now it looks like I'm just combining the two halves. 1/2 times 1/2 is 1/4, and the C and the D remain. Okay, what happened here? How did I get from this one to this one? The 4th is there. Looks like I expanded the C. I substituted in 2 times pi times radius for the circumference. And the reason I chose this rather than 2 diameter was because I was going to substitute 2r in for the diameter. Simplify a little bit. 2 times 2 is 4. 4 times a 4th is 4/4, which is 1, and that goes away. What's left? Well, we have the pi, and we have the 2 radii multiplied by each other, pi times r, which if you simplify, we have area is equal to pi times radius squared. Interesting. So his claim is the area of any circle is half the circumference times half the diameter. Seems like this would be way more work each time than simply starting with this equation. Here's something else he said. If you add 4 to 100, multiply the result by 8, and then add 62,000, the result is approximately the circumference of a circle of diameter 2,000. Oh my. You should pause and see what you can do with that. See if you can somehow write that out and calculate. Add 4 to 100. Multiply the result by 8, add 62,000. The result is approximately the circumference of the circle of a diameter of 20,000. If this result were exact rather than approximate, to what number would pi be equal? Wow, that doesn't seem to make a lot of sense until you try to work this out a bit. So what did I do? 4 plus 100 times 8 plus 62,000. And I got 62,832. Doesn't mean a lick to me. But it says that result is approximately the circumference of a circle of diameter 20,000. So it would seem to make sense that if we use this equation, circumference is pi times diameter, we could substitute in these two values. He says the result is the circumference. So where would that go? Plug that into the front. Of a circle with a diameter of 20,000. So where does the 20,000 go? Well, it goes in for the diameter. So if we substitute that in and then clear the pi, in other words, divide both sides by 20,000, now it makes a little more sense. To what number would pi be equal? Well, do the math there, and we end up with 3.1416. Pretty close. Pretty close. I think the first 4 that, as we use it, is 3.1415 something. All right, this next one's just fun. When asked to write down a number used to measure circles, a backward geometry student named Dill Q wrote that. Do you think he should get any credit for this answer? Explain. Major spoiler alert here. Try this on your own, because I do spell it out here. I just think it's clever. Wanted to point out a couple things. He's a backward geometry student. A backward student named Dilq. Ah, clever. Minor. He's backwards also, and look what he came up with. He wrote 3.14. He wrote it backwards. Why would he do that? Well, he's backward. What other reason might it be? And then, do you think he should get any credit for that answer? Chuckle, chuckle. Finally, set 3 is sticky credit. 3 pieces hinged into a chain. So we've got 2 blue ones and then this yellow shape here, hinged in a chain. If you rotate these 2 downward, we get this square. If you rotate them upward, going back here, rotate them upward, we get this shape. Hint. What do the 2 arrangements of the 3 pieces illustrate? See if you can explain that for some sticky credit. It's kind of clever. So we've got this shape, and then we have this shape. Well, that's it then for lesson 6 of chapter 2. I hope you work this through carefully and you're able to come